Oh, let me get that. Alrighty, let's get started today. We're gonna continue our last little bit of Lewis structures. Hold on, let me get Chrome set up here as well. Cool. Alrighty, so we're gonna continue our Lewis structures. We're gonna finish off that chapter today. Don't forget your exam is going to be next week for this, so it's going to include everything we kind of finish with today. So tomorrow and Wednesday we'll be learning new material that will not be on your exam. But yeah, you'll still be practicing your Lewis structures doing so anyway, so it'll be good. It'll work out. So let's go ahead and let's do a warm-up little here. How about we do let's do the Lewis structure of phosphine, or if we were to try and name this phosphorus trihydride, but typically people just say phosphine, common name for this. If we wanted to figure out its valence electrons, we would have 8 total valence electrons here. We draw our skeleton. We're going to end up with this is our Lewis structure. We have a single bond to each hydrogen, of course, and we have our phosphorus with a lone pair on it. Hopefully, by now, Lewis structures are getting a little bit faster for you guys. And that'll be good because the faster you can get through these, the better you'll be on your exams. Right? One of the dogs is chasing his tail. It's very cute. Alrighty, so with that in mind, let's talk about how electrons are being shared in molecules. Let's compare something like this to another Lewis structure, which I think we've done previously, but I'll just go ahead and provide it for us. Let's go ahead and see, or let's investigate the questions. Are the electrons do these behave similarly? Let's see, how did I write this? Okay, so I'm going to write behaving. Okay. And so we're going to have to look at a property called electronegativity in order to answer this. So if we go ahead and take a look at our periodic table, whatever, we'll do it in blue. If we remember, we had fluorine here was going to be kind of one of those smaller atoms that we have, right? Because it has a relatively positive nucleus compared to something like boron or beryllium or something. Remember, it has more protons, so it pulls things in closer to its nucleus. We're going to see that this property of electronegativity is kind of the opposite of ionization energy. It's not the true opposite. That's something called electron affinity, but we're going to see that the trend is going to be the opposite here. Where electronegativity means it's the tendency of an element to withdraw electrons toward itself in a covalent bond. So we can think of something that is electronegative as hogging the electrons. Oops. So it's going to steal them for itself instead of sharing them equally. And we're going to see that electronegativity is going to increase as we go up, and to the right. So So electronegativity will increase up and to the right. We don't typically include the noble gases in this because they don't make covalent bonds usually, because they already have full electron shells. They don't need to make bonds. So we're going to see that fluorine is going to be our most electronegative element on the periodic table that we typically talk about. And in Discord, I'm going to go ahead and put just a little electronegativity chart, just so we can kind of have an idea of where things are going to be. Actually, yeah, let's see. Let me get one for you guys. We're going to see that there are numbers that are assigned to elements on the periodic table. These are kind of calculated values. On Discord, I've got ahead and posted a little chart for you guys. We're going to see that fluorine is going to be our most electronegative element with what's called a Pauling relativity or electronegativity of 4.0. Oxygen will be our second at about 3.5. And you can see on this little chart here the trend. So fluorine definitely the most electronegative, and then things go less the farther you get from fluorine. So back to the screen. We're going to see that fluorine being the most electronegative, fluorine being the most electronegative will always kind of steal electrons in a shared pair. So if we're looking at something like, I don't know, HF, or we could say carbon tetrafluoride, these electrons are not evenly split between, for example, the fluorine and the hydrogen here. So in this bond, electrons kind of migrate closer to the more electronegative atom. And this is kind of an on average thing. So electrons are always kind of just like floating back and forth, but they're just going to spend more time at the more electronegative one. Because it's got a more positive nucleus, they're a bit more attracted to it. They're going to just spend a little bit more time there. And as a result of the uneven sharing, a partial charge develops. And we use the Greek symbol delta to mean partial. That's a little delta. Oops. It's kind of like an S where you continue to connect it, or it's a little D that you can put a little flare on or something. So lovely. Okay, there's our delta. So we're going to see that if we look at that HF, make it nice and big here, fluorine has an electronegativity of 4.0, hydrogen is 2.1. So we're going to see that fluorine is going to be more electronegative, which it should be. Fluorine is the most electronegative. And as a result, it is going to kind of draw the electrons towards itself. And we indicate this with a fancy little arrow called a dipole moment. That's what this thingy is. I guess I shouldn't use an arrow to point to an arrow, but whatever, it's all good. Where we see that this side of the molecule is going to be a little bit negative. This side is going to be a little bit positive. And so we use this little arrow called a dipole moment to show this. And so the dipole moment there shows you where the electrons are being kind of attracted to. So the electrons are going to be moving more towards fluorine, which is going to give fluorine a little bit negative charge overall, not a full one, partial one. And hydrogen will get a partial positive charge. Again, not a full charge, but a partial one, so less than a normal charge. And this little dipole moment arrow has a little kind of hatch, I guess, on the back to show the positive side, and then the arrowhead is towards the negative side. So just if we're looking at the dipole moment arrow, this side is the positive side. Since it's got the little plus part, and this side is always going to be your negative side. All right, and so we're going to see that this this will happen when you have a difference of electronegativity in a covalent bond. If there is a significant change in your electronegativity between your atoms, we'll see that you're going to end up with this sort of polarity. All right, so if we go back to that original thing where we had drawn the phosphine and the phosphorus trichloride, oops. We're going to see that we can kind of look at these bonds, and we can go ahead and look at their electronegativities. So here, let's go ahead and look at the table here. So phosphorus has got an electronegativity of 2.1. Hydrogen has an electronegativity of 2.1. Chlorine has an electronegativity of 3.0. And phosphorus we've already seen. And so hopefully we can see there's definitely a difference here, right? We can see that the difference of electronegativity between here, 2.1 minus 2.1 is 0, whereas the difference of electronegativity here is not 0, right? It's a pretty big number, 0.9. As a result, we're going to see that with our example here on the left, the phosphorus-hydrogen bond, electrons are going to be shared equally. So there is no difference in electronegativity there. So neither of these atoms are going to kind of steal the electrons, and so things are going to be shared equally between them. So we have no partial charges in this molecule as a result of that. Because everything is being shared equally, there's no uneven distribution, so there's no fake charges here. All right. In the second one, the phosphorus-chlorine bond, we can see that the electrons are attracted to Cl more. And so we're going to see that if we want to indicate that, we can use our dipole moment arrow to show that we have electrons moving towards the chlorine side of that bond. We could also indicate our partial charges there. So the more electronegative one is going to get the partial negative because it's going to be attracting the electrons. So more electrons, more negative. And the phosphorus will be less electronegative. It's going to be the one being stolen from. So it's going to become a little bit positive. And so we'll see that phosphorus is a little bit positive. Chlorine is a little bit negative as a result of this. All right, and we would call this we would be able to say that a phosphorus chlorine bond is a polar bond. We have poles on it, just like a magnet has north pole, south pole. A planet has north pole, south pole. Here we have a negative pole and a positive pole. So there are two poles here, positive and negative, and so we call this bond type polar. All right, and so this is going to arise when you have a difference of electronegativity that is sufficient enough. So let's take a look at what we're going to kind of classify these things as. So in reality, it's kind of a spectrum. There's not really a hard and fast, this is polar, this is not polar. But we have some kind of general guidelines. So if your electronegativity is between 0 to 0.4, the difference between them, so if you just subtract their electronegativities, we're going to call this a nonpolar covalent bond. This is kind of a rough idea of where we're going to draw that line between something being polar and not. So we're going to include 0.4 here. All right, and if you're between 0.5 to, say, 1.9 or so, that's going to be a polar covalent bond. And so this is just the difference of electronegativity. Here, I'll write that out just to make sure. Between the two elements. And if you're bigger than 1.9, that is just a purely ionic bond at that point. So if you see something like sodium chloride, you're definitely going to get into an ionic bond there. You're going to see the difference of electronegativity is 2.1. That's bigger than 1.9. We know that's pretty much an ionic bond at that point. Though in reality, these are kind of a spectrum. Kind of. The best way to describe it, though, is the bigger your change in electronegativity is, the more polar you are. Not you, but the bond is. So, again, kind of a rough idea here of how we're going to classify some bonds, but I mean, there's no reason that we can't say something with 1.9 would be polar versus ionic. It's kind of a gradual spectrum. There's no like, okay, 1.9, now you're officially ionic. That's kind of where we draw these lines, but in reality, again, it's a continuous thing. So let's go ahead and look at a couple of examples here. How about we look at these three bonds and determine if these are going to be polar bonds or not. And how we're going to do that is we're going to go ahead and look at their electronegativities. So if we go ahead and look at that table I've given you guys, we can go ahead and write these out. And then carbon 2.5, hydrogen 2.1. Okay. So if we look at the change of electronegativity, it doesn't matter which one you do. Just take the absolute value of it, whichever one you're subtracting. It doesn't really matter. So if we're going to do these, we can do the math, I hope. And then the last one. Okay. Ta-da, we've done some math. So let's go ahead and look at our chart, or not really chart, but yeah, it's a chart. And go ahead and see where these are going to lie. So the first one we had was 0.9. So that one's going to be kind of smack dab in the middle of our polar covalent category. So we know this is for sure going to be a polar bond. And we're going to say that this one will also fall under that category. We're going to include 0.5 as polar. And our last one was 0.4, which we're going to count as nonpolar. So that's kind of where we're drawing that line. So about 0.4 is where we say it's nonpolar. Above that, we start saying it's polar. So, and then if we're going to look at kind of the magnitude here, we can say that the NH bond is more polar than the OF bond. And that makes sense, right? We have a greater difference of electronegativity between nitrogen and hydrogen than we do with oxygen and fluorine. And so we're going to see that that will be a more polar bond. And that means the partial negative on nitrogen is larger than the partial negative on fluorine in these particular bonds. So the bigger your polarity or electronegativity differences, the more polar you are. The more polar you are, the greater these partial charges become. And as we see, once we get to around 1.9 or so, they become full charges. So they're not partial charges anymore, but they're full charges. And so we're going to see, again, it's kind of a spectrum where we're going to be just kind of making it the partial charges bigger and bigger and bigger. Eventually, those reach to a full charge. So that's kind of how we're going to be looking at those. Alrighty, any questions on that? This kind of hints towards the whole point of doing these Lewis structures is if we can talk about the polarity of bonds, then we can talk about the polarity of molecules as well. And as we're going to see in the next chapter, that whether a molecule is polar or not is going to greatly affect its physical properties and how it interacts with various other chemical compounds. All right, not seeing any questions so far, which is cool. Let's look at molecules overall. So we've talked about bonds now. Polar or non-polar. But molecules can also be polar or non-polar. And we're going to see that this greatly depends on symmetry of a molecule. For example, if we look at our good friend carbon dioxide, here it is, carbon dioxide, we know that carbon has an electronegativity of 2.5, oxygen has one of 3.5, so we know for sure that a CO bond is polar. That should hopefully not be a problem. We can see that the difference of electronegativity there is more than 0.4. It's 1, right? And so we can say, okay, yeah, this, oxygen is taking the electrons away from carbon. Oh, but look on the other side, we have the same thing happening. This poor carbon in the middle is being pulled from both sides. And if we remember anything about vectors in physics, that if you have two forces pulling on opposite directions, nothing's going to change overall. So we're going to see this carbon its electrons are being pulled in opposite directions. Right? One oxygen is pulling those electrons to the right, the other oxygen is pulling them to the left. And since it's the same thing on both sides, we have an oxygen on one side and oxygen on the other side. Let's include that. And both oxygens pull with the same force. Overall, no electrons move. So, this is something I often would do in person, is I would ask two of you to come up and pull me from opposite sides. Like, I would just stick out my arms, you pull me this way, you pull me that way, and we're going to see overall, if you're pulling with equal strength, I should not move, because you're pulling me with opposite directions. So these dipoles will cancel each other out. So that oxygen on the right wants the electrons, but so does the oxygen on the left. And since they're both the same, one oxygen is not stronger than the other oxygen, nobody wins. So neither oxygen ends up with extra electrons. And so overall, even though an individual carbon-oxygen bond is polar, overall, CO2 is a non-polar molecule, despite the fact that a CO bond is polar. So, we're going to see that they're related to each other, this idea of polarity of a bond versus a molecule, but they don't necessarily mean the same thing. So you can definitely have a nonpolar molecule that has polar bonds in it. And you can also have nonpolar molecules that have nonpolar bonds. And of course, you can have polar ones that have polar bonds too. So, and polar ones that have nonpolar bonds. You can have all sorts of mixtures here. So, suffice it to say that the presence of a polar bond in a molecule does not itself predict the polarity of the molecule. So again, we can have polar molecules that have nonpolar bonds. We can have nonpolar molecules that have polar bonds. We can have all sorts of different combinations. So just identifying a single bond as polar or nonpolar doesn't tell you about the molecule by itself. You need more information. And we're going to see that the biggest factor in predicting the polarity of a molecule is symmetry. And so we're going to see that if all electron domains on a central atom are identical, you will end up with a nonpolar molecule. And that's going to kind of be our main thing here. We're going to need to see that all the electron domains are going to be of equal strength. If they're all identical to each other, we're going to see that overall we'll have a nonpolar molecule. So let's go ahead and take a look at some examples of nonpolar molecules. So methane is going to be a nonpolar molecule. The carbon tetrafluoride that we talked about earlier, also a nonpolar molecule. These are all nonpolar molecules. These are all non-polar molecules. Because we're going to see that because of their symmetry, if there is any bond or polarity happening within a bond, it's being canceled out by other bonds. So if you imagine this carbon tetrafluoride, electrons are going basically in all four directions here, and they're all going to just cancel each other out. So all the fluorines are tugging on that carbon. Nothing overall is going to happen. If we go ahead and take a look at, as always, my good friend Wikipedia. Such a great tool for teaching. I don't know why, like, like high school teachers hate it, but it's a fantastic tool, especially for science. There's such good information here. If we go ahead and look, overall, this stuff on the right tells you so much, by the way. You can always look up the molar mass. You can look up all these physical properties about things. But right now we're interested in the dipole moment. So notice it has 0 as its dipole moment, despite the fact that we saw... Oh, I guess we looked at carbon tetrafluoride instead. We can look at that in a second here. But notice that even though a CCl bond should be polar, this one is not going to be overall polar because all those chlorines will cancel out. So we're going to see overall its dipole moment is 0. So here we can look at carbon tetrafluoride instead, which is the one I guess we had originally looked at. Again, we're going to see its dipole moment should be 0. All right, because it's completely symmetrical, everything is going to cancel out. However, if we throw in something like this, where now we have different electron domains, we should see that this molecule overall will be polar. And indeed, we do end up having a dipole moment associated with this molecule. As we can see here, it's not 0, indicating that the molecule is polar. So thankfully for us, if something is polar or not, it will have a dipole moment that is not 0. And so we can see here that by having different electron domains with different electronegativities, we're gonna actually have a polar molecule. And interestingly enough, our phosphine example, where we saw that the pH bond was nonpolar, take a look at this. Where is its dipole moment? Aha! Notice, even though phosphine had completely nonpolar bonds, there are other factors at play here. And again, we're going to see that phosphine should have a lone pair on it. And a lone pair is not the same thing as a hydrogen. And so as a result, we're going to see that the symmetry is going to be the most important part in identifying whether a molecule is polar or not. So again, here we're going to see that we have a dipole moment here. And finally, let's look at this compound here, though I guess we have to actually look at the chemistry one for water. Let's go ahead and find its dipole moment. Notice its dipole moment is especially large. That's something that's important for us. we're going to see water is a very polar molecule. Notice here, Wikipedia does have all of that same fancy information. I guess I shouldn't be telling you this, given your exam is next week and you're going to have to tell me about water's geometry, but that's okay. That's okay. I will allow it. So, use tools that you have. So, cool. So, anyways, there you go. So, those are some examples of things that we would see are polar versus non-polar. Oops, go away. And so all of these ones that we've drawn here are non-polar because they are completely symmetrical. So to identify if a molecule is polar or not, this is what you have to look at. If everything is the same, then it's non-polar. If anything is different, it's polar. Easy. So let me write that down. So if any electron domains are different, the molecule is going to be polar overall. So we saw with this example of dichloro-difluoromethane that this was polar overall. And if we were to say look at something like this, we see oxygen and hydrogen are not the same. Those are definitely going to be different domains. So, and then a lone pair, remember, does count as a domain. So here we have chlorine is not the same thing as fluorine. Hydrogen is not the same thing as oxygen. And hydrogen is not the same thing as a lone pair. So all of these are going to be polar. So we have domains that are different on our central atom. And so as a result, we're going to see that these are going to be polar molecules. Hold on, the dogs are doing something really cute. They're all squished together. Like, there's all these beds in here, but they're like, nah, I want to be all squished up. Let's get a good picture. I'll put this up in Discord for you guys later, so you can enjoy that. So, this is going to be the easiest way for us to tell if something is polar or not. So if you can come up with its Lewis structure and identify if anything is different, it should be polar. That's what we're going to expect. And so, as a result, we're going to see it all comes down to symmetry. So symmetry is our biggest kind of factor here. All right. Any questions so far? We're moving through this pretty quickly. This is a little faster than I had intended to go, but that's okay. So let's just do a couple of examples then. So, okay, we'll look at this. One thing also I guess I should mention, while I can't think of any particular examples, or here, let's take, remember we had that kind of resonance form of carbon dioxide that would look like that? That was one technical way of looking at it. Remember that domains do not care if they do not care about the bond order. They don't care about if it's a single, double, or triple bond, whatever. So even if carbon dioxide were to look like this, it doesn't matter. We only look at what is on this central atom. So we're going to see that this would still be nonpolar overall. Bond order, remember, would be single, double, triple bond. Does not matter. Doesn't matter about your bond order when you're looking at something's polarity. All right, so just keep that in mind. Okay, let's go ahead and like move this down somewhere else, just so we have some room here. Let's just like throw this all the way down here. Okay, cool. Whatever, it's down there. Cool. So let's look at this example. So we have two questions are being asked. This sulfur dichloride molecule, does it have polar or nonpolar bonds? And then is it a polar or nonpolar molecule? So again, these two questions could have different answers. They could have the same answer. So we'll see. So let's go ahead and actually get the pen out. So let's look at the total electrons here. We should have 6 plus 7 times 2, which will be 20 valence electrons total. We'll go ahead and indicate or put our skeleton in here. So we've used up 4 electrons, 16 left, 2, 4, 6, 8, 10, 12. Just use 12 more electrons. We have 4 left. We give them to sulfur. We double check. Everybody is happy, and indeed they're all happy. So we have our Lewis structure here. And we can go ahead and redraw it with the bonds here. This is why it's important that we don't forget our lone pairs, because that's going to be very important here. So let's go ahead and look at an individual SCl bond. If we look at their electronegativities, sulfur is, actually I don't remember, let's look it up. Sulfur is 2.5, I lied. Okay, 2.5, and chlorine is going to be 3.0. And so the difference of electronegativity is 0.5, therefore. So we are indeed expecting that our sulfur-chlorine bond will be indeed polar. And we're going to see that because of the geometry of this, it's kind of drawn linear right now. So if you were to keep it as linear, you were to draw this, you might be convinced that overall it's going to be nonpolar. But if we redraw it with the correct geometry, so remember a bent angle should have something like this. We should have less than 109.5 degrees between them. We can see that in fact these arrows do not cancel out because they're not pulling in opposite directions. They're going to be pulling, both of them are going to kind of be pulling, they're still pulling on sulfur, but we're going to see overall they won't cancel out because they're not pulling in opposite directions. One of them's pulling a little bit down, the other one's pulling just to the right, so they don't cancel each other out. We could also have just looked and said, okay, you know what? A chlorine is not the same as a lone pair, so this should be a polar molecule. And indeed, we would see that overall, this sulfur would be partially positive, and these chlorines would be partially negative. And we're going to see that if we were to just look at this molecule, let me erase our electrons here. Oops. Just to have some more room. If we're to just redraw this again, making it a little bit more obvious. we're going to see that overall, this half of the molecule will be a little bit positive. This half of the molecule will be a little bit negative. Hold on, I dropped my stylus. Okay, there it is. We're going to see if you were to add the vectors up, if we have a vector going that way and a vector going that way, overall, if we add those up, we have one just pointing up and down. We don't have to worry about doing the vector addition in chemistry. That's something we'll leave for physics to do, but or for math. But suffice it to say that overall, your overall dipole would look something like this, where it's just up and down if you were to add those two arrows up. All right, the left and right stuff would cancel out, but the up and down part is not canceling out. So you're left overall with a polar molecule. Let's not forget our lone pairs there. All right, so to answer the question, we have polar bonds, and it is a polar molecule. So we know it's polar bonds because we had a difference of electronegativity that was 0.5 or greater. We know it's a polar molecule because a chlorine is not the same thing as a lone pair. So that's gonna be our kind of shortcut. But if you really wanted to be, the most correct about it, you would draw the arrows and see that they would not cancel out if you're using the correct geometry. So, exciting stuff. All right, and I guess I've kind of still, I guess I put this in just the right spot. We had just enough room. So just remember again, this would still be nonpolar. Over here, we don't care if something is a double or triple bond or a single bond. We just look at the identity of what it is there. Alrighty. Any questions on the last example or on this idea? All right, little dude. All right, then let's look at one more. And then we'll call it for the day, because that'll be, we're done with the chapter. Let's look at chloroform. Which is CHCl3. If we're to come up with its Lewis structures, we have its valence electrons is going to be 4 plus 1 plus 21, which is 26 electrons overall. Put the skeleton together. Doesn't matter where you put the H versus the CLs. Okay, we're going to use up 8 electrons. We have 18 left. Those 18 are going to go to the chlorines. Remember, hydrogen is already happy with 2. It does not need more. So we'll have nothing left. If we redraw it, let's go ahead and look at these bonds. We have two different bonds here. We have a CH bond and a CCl bond. If we take a look at their electronegativities, we're going to see that overall this would be 0.4, this would be 0.5. We classify that as polar and this one as non-polar. Hi, little dude, I'll pick you up later. I'm almost done. So, we're going to see that this molecule has a mixture of polar bonds and non-polar bonds. And so, as a result, all of these chlorines are going to be pulling on the carbon, but the hydrogen is not. And we're going to see that overall, we can see very clearly we have kind of that left half of the molecule is going to be the polar part, right? That's where we're going to have a negative charge on the left because that hydrogen is not pulling on the carbon. So overall, this should definitely be polar as a molecule. But we also know that a chlorine is not the same as a hydrogen, so we know it's polar already. You don't even have to think about arrows. I know this is technically not the correct geometry. We should do this tetrahedral in 3D, but suffice it to say, the up and down arrows can cancel themselves out, and now we're stuck with a left arrow. Since there's still an arrow left over at the end of the day, it's a polar molecule. So we can see here that this molecule is a mixture of polar and nonpolar bonds, and overall this molecule is polar. All right, it looks like most of the examples we've done have had the most electronegative atom being in the on the outside. If we go ahead and look at something like water, though, we see that the OH bond difference is going to be 3.5 versus 2.1. 1.4, very polar bond there. We see that, in fact, it's going to be the central atom there that is going to be the one that's negative. And so overall, we have the positive part down there. So your central atom could be the negative or positive. It just depends on its electronegativity compared with whatever it's attached to. That being said, though, typically your central atom is going to be the less electronegative one. Oh my god, they're even cuter now. So typically that's the case. Oh, but we're going to see that sometimes your central atom will be the more electronegative one. So that being said, we are done. So we're done with chapter 5b. So your Lewis structure homework does include bits on polarity, as well as the molecular shape stuff. So make sure that you're doing that. That's due Saturday. Notice that is different from our usual Sunday because I want you to look at the answer key on Sunday. So I've already put the answer key. It's going to become visible Sunday morning. So after you submit it on Saturday, you'll be able to look at the key and you'll be able to see if you've gotten the correct answers or not, so you can use that to study for your exam. Monday will be our exam. It'll be the kind of same format as last time, multiple choice on Canvas. You'll have your time limit. It'll be about 30 questions or so and about the same amount of time. What was it, 75 minutes last time? So plan accordingly. I would definitely recommend practicing these Lewis structures because the more you do it, the faster you get at doing it. And that can make or break your experience with that exam. So don't forget, we're going to have everything from 3B to 5B in here. So that's going to include our empirical formula and mass percent. It's going to include our nomenclature and our ions and that sort of thing, as well as this Lewis structure and polarity stuff. So a lot of information here. So study well. You have a week until the exam, so get on that. Stuff that we start tomorrow, I'm not going to make your homework due this weekend because I want you to focus on your stuff that'll be on the exam. So stuff that we cover tomorrow and Wednesday that is not on your exam, I will put homework up, but it will be due next week. So not this coming weekend. So cool. Thursday, if you want, we can do another exam review. So come with questions. You can post them in our review questions channel. If there's a, hey, can we go over this on the homework? Or, hey, can we do another example of identifying a polar molecule or something? I'd be happy to go over those on Thursday. So we'll do that. We'll have our Q&A on Thursday. Alrighty. Well, with that, enjoy your Monday. I'll see you tomorrow. We're going to start talking about intermolecular forces. Very exciting stuff. Alrighty. Enjoy your day.